glad to be back again at Stanford. A little bit about myself. So as Mark said, I did my PhD, we published a lot of papers, but the second part, part of my career, I was building companies. So one company I built was called Catapult. If you go to Amazon, you can buy Klarna, Affirm, Catapult, it went public. I did another company, and now we have started Torque AGI. So today's talk is about how to use AI for robots, but also use it in a way that can see and make real use cases in the real world, right? So this talk will be a mix of what robots are doing in the real world with the foundation models. So we'll talk a little bit about, this first part is obvious, right? Physical AI is making robots smarter, right? You're seeing a lot of demos, a lot of videos. Data is obviously very, very important, but the core message of the talk is that physics is a very important contributor to robotics intelligence, to physical intelligence. So when we are building models in digital AI, that's very different from building models for robots. And there's a systematic and nice way that we have all to build to get harness the full capability of the AI. And this is happening because AI has a whole generational upgrade. I'm stating the obvious, right? Digital AI is sitting on at least 40 years times 10 billion years of human data knowledge. So digital AI has a lot to build upon. Waymo is not quite using the latest generation of physical AI. They're moving towards it, but it's one proof point that, okay, in our common lives, in our everyday lives, now you can actually sit in a car in San Francisco at least, in Arizona, and go from point A to point B. But what we are going to see more of it, and not just see, most of you are going to be part of it, is that how are we bringing it all to robots? Now at Torque AGI, we are focusing on enterprise robots and bringing it there. And the type of robots that we are working on are really focused on enterprise tasks, because these we believe will see the first mass production and usage of physical AI, because these environments are used to machines. And if you add AI to it, it's possible, and it is happening, that you can see more and more applications. So whether it is dexterous assembly, moving materials, construction, agriculture, distribution, this is a very exciting area. And this is very important, right? Like we were working with a medical foundation company. Like most people don't realize that 70% of food produced is wasted, not because of production, but because of distribution. If you don't timely get it to the people in the right point in time, that food just goes to waste. During COVID times, medicines were just sitting at ports, sitting in warehouses, they were lost. So this distribution and these kind of tasks are very, very fundamental to our survival. And this is something that I'm excited personally to solve, right? And that's why we are doing this. And from a market perspective, what happens is if you are able to find huge opportunities and create value, this is not a zero-sum game. When a new opportunity arises, when you're looking at a whole new area, which Jensen Huang says is 30 trillion, Elon Musk says 60 trillion. Well, when we did the calculation, it was 250 billion. That's fine, but these are large numbers, and these numbers are very simple calculations. You multiply the number of tasks that a human cannot do, or a robot could do better or augment a human, that number comes out automatically. And this is very exciting. We should be solving these real-world important problems. So that is why we put together a team at Torque AGI, where we have many of us from Stanford. We love Stanford, but we also have people from SpaceX, from many other places. And the team we have built is frontier tech married with people who know how to do reliable engineer. One of our engineers is very proud that he actually exploded 4 rockets over 4 years at SpaceX, and he launched the 5th one. So the point being, reliability is important when you're building robots for the real world and married along with the business. What we are really building at Torque AGI is like, this is like, in some sense, is similar to a couple of other efforts going on in the area, right? Like you can actually build very much like OpenAI, one single model, and have thin interfaces and workflows based on that model for numerous applications. So that is the change from historical times, some of you may have been using in that, be aware of that direction. In 2010, before even deep learning came, there was a separate sentiment detector, separate this detector, separate that detector, but now there's one model from OpenAI, one from Anthropic, and you're using it for various purposes. And that has many benefits because knowledge is shareable, right? That is why this is valuable. So let me take you a little bit back and kind of walk you through what was going on when we were building the AI models. So the reason, the basic idea behind data-driven AI, which you can call it machine learning, was that you can apply it to completely new problems that you would otherwise think are not solvable. And if you are able to formulate a couple of things very well. The first problem is, can you articulate what's the input and what's the output you want? That's the first step. Second step, if you are able to say, get some training data in place. And the third thing that if you're able to say is, that's some mathematics, right? You have to be able to say, what is the loss function, or what are you trying to optimize for? So input, output, what are you trying to optimize for, and data. If you put these three things together, then suddenly you can completely unlock seemingly unsolved problem. So back to Stanford when I was working with Andrew Ng, in 2004, when I started, this problem was considered unsolvable. It's like a single image, it's an ill-formed problem. You cannot take a static single image and create a depth out of it. So what we did is we framed it into a problem that this is the input, this is the output. At that point in time, there was something called Markov random field or conditional random field. These are very shallow models. Basically think of that as a small graph over which you are expressing a cost function. And now with this model, we were able to feed a certain amount of data. In those times, a couple of thousand data points was a lot of data. So we used it to train the model. And then given a lot of examples like that, you didn't have to explain to the model that, oh, this is a sky, this is this, this is that, right? It is learning it over this graph. It's understanding that some image features, blue is a sky and green is grass. And if two things are next to each other, that's the edge on the graph. And this form of expressing what you want to the AI is the first step. So you have the input, you have the output, you want to say what you want. And this allowed us to basically build this model, and we applied it to fly drones in the university campuses. We applied it to some navigation and mobility examples. Later on, the models became more powerful. So this is from about 2009 and 2010. Now think about, instead of having a simple loss function or a 2-layered or 3-layered architecture, you can have 16-layered architecture. That was like one form of instantiation of that idea was convolutional neural networks. So you're creating stacks of modules with certain functional properties, but the basic idea is still the same. You needed data, you needed to define what's the input and output, and someone had to express to the model what is the loss function, which is what are you trying to optimize for, right? But by doing that, it unlocked a whole decade of new opportunities. Now you have perfect grade OCR, like even your post office is now using OCR to route your messages. No one is reading your addresses, right? That was the first basic practicalized example of what happened. Numerous image detection opportunities opened up. The whole applications that you can build on your iPhone using cameras became democratized. So many apps are now using this CNNs at the back end. And robotics is also caught up. So most of the stack at most of the robotics companies is built out based on CNN from the perception side. And what it does is that it allows you to completely address new problems. All you have to do is to collect a lot of data, feed it to a network, and say, oh, this is what I want to optimize for, right? In my previous company, what we were doing is we applied a similar idea to basically track people through radar sensors. So we were able to take the radar sensors, track people from it by training a model. Then we trained deeper model, and with that deeper model, we were able to extract respiration rate from radar sensors, because when your chest moves, you can breathe. Then if you could get a little bit smarter and the person is not moving, then you can extract pulse rate also. So this AI, we were able to get to FDA as a FDA Class 2 status, and now it's being installed in numerous homes and hospitals and facilities. And more recently, over the last 3 years, we have been connecting it to deeper models which have a much larger amount of context. So one thing that we are very happy about is that in so many cases that we are seeing, a doctor or a nurse never had the time to figure out context of the patient. So think about a doctor. They come in, they look at your chart. If someone flagged something, they will notice it. But they have 10 minutes. They are super busy. And there are so many mistakes which you would be surprised that happen. They give a wrong medicine, there's a medication reactions, people get sick, all that, right? But now medicine and health is one of the places where AI is having a deep impact. And we did it using sensors and in-home monitoring. So moving on, the problem with these approaches that we kept on hitting was the data problem. So when we were working with some of the text or online use cases, it was relatively easy to say, oh, just go on, look at, I don't know, 1 million of EHR, electronic health record system text, and figure it out. So AI had something to work with. But when you're dealing with physical world, the answer was, oh, well, we don't have enough data, so why don't we spend $10 million? Or in research universities, it's a joke, but first quarter or couple of months of projects for each of us was go collect data, right? And which we still have to do, but that data itself didn't seem to solve the problem, right? How many people are aware of the Tesla self-driving thing? Most of you. And how many people have taken the Waymo robotaxi? All of you. This is amazing. But think about it. 10 years, they did that. Why were they able to do it? Why Tesla was collecting all this data for last, 7 years with their camera setup? Waymo had $20 billion or maybe $50 billion of, and majority of that went to data collection, by the way. The cars only recently came out. Now, when you think about how do we solve the world's food and agriculture problem, the problem is not that the food cannot grow. The problem is not that the tractors are not working. The problem is you can't find people on a Friday night for harvest. The harvest goes to waste. And the reason tractors cannot work is there's dust. There is long tail edge cases. And we do all hear about these edge cases in self-driving environments, which is, oh, Tesla car crashed. And well, we hear about it, get sad about it. The problem is this style of approach is not entirely suited for physical AI. I don't think that data alone and just data-driven AI is the solution to this problem. We need something else. Because what happens is in this case, now someone has to go around and find at least 100 or maybe 1 million or maybe 100,000 of such cases to train the model. And this is not sustainable. Like, how are we going to get our underwater robots, our space robots, our mining robots, our household robots to work? This data collection is just not going to be possible. So looking back again, one thing that we did in a long time back is we were trying to say, okay, let's solve a hard problem. And we found that we were all very hungry in grad student times. So like, okay, let's get a robot to cook food. So we had a lot of free food. The problem to solve the problem was when you're trying to get a robot to solve a task as physical at this task as cutting a food, which is actually really hard. So think about for a moment that if you are wearing rubber gloves in a wintry environment in Michigan, thick gloves, right? You cannot even put a keychain in your door, forget about doing anything else. And this is happening because robots are living in the physical world. So the challenge task that we picked up, I think it was about 25 different food items, and the robot had to cut it with a single model. And we kept collecting data. I don't know how many cucumbers and these things we cut, but that data was not solving the problem. So we said, what else do we need? Well, we also tried other things, right? We were doing other projects in parallel at Cornell University. We were like, okay, let's just watch millions of YouTube videos and data and so on and so forth, right? Because there's a lot of information in the recipe videos. You can actually watch videos to say, oh, cook this, stir this. And we were able to take that data and learn a model that had the joint representation from language to vision to action, robot action, into the same space. So this is the outcome of the first round of learning, where each point or cluster of points is representing the embeddings from completely different modalities, completely different robots, completely different data sources. So you are looking at something coming in, which is 3D shape. You are looking at something coming in, which is the image, and the text that you cannot read is about, oh, turn the handle in this way, it will do something. But the nice thing that happens here, which is now VLA models that you are using, the real reason, I think the real benefit of those models is, if you learn something from one modality, it directly transfers to the other modality. That's the benefit. So if you learn about one concept, and let me explain it from language example. If you are learning if you have learned a large LLM, if you have learned a LLM, and you have learned in it the notion of adjectives in English, and you start talking in French, you don't have to retrain and explain the notion of adjectives in French. So that's actually very surprising, right? You have learned a notion, you may not have seen that language before, but you can still transfer the concept. And that's why some of the latest researchers are now able to decode Sumerian languages, for example, right? Because the linguistic structures are still intact. And same thing happens with physical structures. But it learned a lot of things, but it still didn't learn enough to cook. So the problem was, one of the problems we found was, when you're learning, the embodiment of the models, for example, on the YouTube videos is based on humans. Humans act in a certain form factor. So while the video data is usable, there is still some out of distribution context, things are shifted. So you cannot immediately or easily transfer a data that is collected in a different domain perfectly to a new domain. Now, there are two solutions to it. If you had 20 years, $10 billion of human knowledge online, as it is the case with digital AI, like how many books are there in English and French, you can basically throw data at it, and at some point in time, it will start learning, right? But that is not going to be the case with physical AI. The amount of data requirements is insanely large. So the solution that we found in those cases is, why don't we, for this purpose of cross-embodiment, start doing something else? So even if we look today at the latest school of models, whether it is robotics transformer, the large behavior models, I think they are still missing the point. The point they're getting is that, okay, great, let's embed the vision, language, and action in the same space, but they're missing the point. It's physical AI. You have to consider physics as part of it. And we have tried, right? We have tried 10 years back, we have tried 5 years back, we have tried 1 year back. And what happens if you don't understand physics is, you can kind of get the demo to work. You can train a policy, you can do the embeddings, you can feed it in a certain manner, you can connect it. And when the robot is trying to do something even slightly conceptually different, it just doesn't seem to get the point. So how do we deal with this, right? So this is where I believe that I think the physics is the key, right? I'll pause here to see if there are any quick questions so far. All right. So how do we encode physics in the model? So let's look. One of the ideas is that we explored is, how do we start with kinematics? Kinematics is the one basic form of physics, which in case of robots, with humans, with known 3D models of the world, you know it, in some cases to very high degree of precision, in some cases to approximate precision. And that's the problem with the competition or the philosophical argument between hard physics and data. If you are using a traditional model like model predictive control versus a data-driven model, at the first blush or as they stand, they seem incongruent. One of them is hard mathematical equations, precise things, programmatic way of doing things. The second one is that you ignore all that and you put that into a model and hope it works, right? So what we found is that we can do both. We can do both. So this is a very simple example. We applied it to numerous examples from human activity understanding, robotics videos, and so on and so forth. So imagine that this is a human being. A very simple illustrative example would be this human would have a head, it would have two hands, it would have two legs. That's a kinematic form factor, right? The walking part of the human is related to legs. There is certain graph independence that is going on, right? Like what your head is doing has very weak level of dependence on walking, kinematically speaking, because you can tilt your head, it doesn't make you fall, right? What your hands are doing on the body, even though it's whole body manipulation, it is less dependent on the other aspects. So if you draw a graph out of it, that makes a representation. The second thing that you can do is that take that representation of the graph and create a isomorphic transformation where each node in that graph is on the first row, each edge of the graph is in the second row. That's just an isomorphic transformation. That is just going from here to here. And now you see all these boxes. Some of them are representing nodes, some of them are representing edges. So when we published this paper 2017, at that point in time, we had LSTMs, couple of different models, very early versions of transformer models without attention, which are not exactly transformers, but they were just large models. But the nice thing that happens is now you can express those loss functions and models over this graph. Or in other ways, you can take this graph and use different parts of the model. So there are a couple of different ways of doing it, but the idea is, one way to explain this idea is that you have a model that is worrying about the spine, the other one about the arm, the other one about the leg. This edge, which is related to arm and leg together, is worrying about how arm works together with your hand, right? So in illustrative ways, what happens here is you have a model on the left, which is trained on a human with slightly different kinematics. The middle one is a different human who walks fast. This is again an illustrative example, right? When you apply it to real world examples, the physics will be more complicated. Now you have two models, and the human is walking slowly on the left, so it's walking slowly. And now if you recompose the model, interesting things happen. Now you can have a human which is basically half fast and half slow. So this illustrates that you can do a transfer through different kinematics here, and the whole model still works. So now we have taken this idea and applied it in the VLAM framework, in the agentic framework. So this is what we are doing at Torque AGI, where we have, obviously there are three steps to the process. There is the embeddings or encoders, which come from the left side. You have the inputs to the model. It could be robot data, it could be haptic data, it could be 3D data, it could be different kinds of data that go in from the left side. Now the model is really the entity which is effectively minimizing some form of a loss function, right? Essentially, and it's a large model. The right side are interfaces to the model called agents. Now you have all three, and that all three by itself is not new, right? That is what any architecture of an agentic workflow with a model will look like. You have ChatGPT model in the back end, and you are using the text interface to access it. You can write API agents on it. The interesting thing is that now what we have done is we have encoded different forms of physics into each of these steps. So the kinematics decides how the things are encoded inside the model. Kinematics changes the attention and the way the model is used. There are tools that we have pushed into the GPU grade at the microsecond level. So the model itself has a kinematic simulator, inverse kinematic simulator that can do things at microsecond level. So reasoning loop is much, much faster inside layers of the transformer stack. And then you have soft physics. Some of the concepts are not expressible as purely kinematics. For example, soft contact things, stacking concepts, and gravity, those are encoded as a small neural network, which is again accessible to the network. Once you have all the model like this, you're minimizing some loss function, which basically provides the cross embodiment. The one more thing that we have to do is one of the challenges in the model is that you cannot be running today's model by default at a real-time speed, which is very, very necessary for our robots to function in the real world. So the nice thing is that in partnership with NVIDIA, now it's possible to do most of the model and data in the GPU. So everything is in GPU memory, everything is in the GPU model, all the parameters, all the data. And then you can design a method where the agents are a thin interface, very thin interface in the CPU, which are using the model in the GPU appropriately. So you have pointers, you can stack them, you can flow them. And this part is very intricate because for robots, the time to first token in real-time performance is critical. Like the models have to run on the edge. They have to return in 100 milliseconds, otherwise the robot will get stuck. In some cases, even faster, right? So in this case, what we did is, these are some of the examples. So the robot on the left, the task was, hey, robot, can you manipulate the box? And now you think about the problem, we did not give it 10,000 examples of folding the box. We gave it probably 10, only 10, because it has seen much of other things. And the reason it's able to do this job is, first of all, it knows its own kinematics. Number two, it has a decent notion of articulated objects in the world. Most objects are articulated. They have some level of articulation. If you put the two together, now it can start reasoning about, oh, I have to fold the box, and if I understand the flaps, I push it down. But from those few examples or from the data, if I don't push it down long enough, the flap will come out again. These are finer details, but if you, next time you fold the box, you will realize you're subconsciously doing things very hard for kids to do. So that is something that, one of the tasks that the robot ended up doing. In another example, this is why we were able to do the food cutting example, because it has mapped the food looks like this, the haptics looks like this. In a graph architecture, the node that relates to the end effector and the haptic motion is a separate part of the network. You can change the whole robot in the back. If your end effector is the same, you can still reuse the robot for that task. And this is why we were able to cut like 25 different food items with very, very complex cutting motions. And then you can sequence it together in a longer task. So this is something at that point in time we were not able to get very high performance on. There was one more problem. So in this case, the person is asking the robot to, this robot is shot around 2015 to make ice cream. So the robot goes around, looks at the environment, it takes the language, goes back to the model, figures out the closest embedding in the visual space. It says that, oh, affogato means I have to get the coffee out, this box is there. And we were doing it over a bunch of different tasks downloading from the internet. The problem is that the video is sped up almost 20-25x, so by the time the video is finished, the ice cream was melted, so we couldn't eat it. so now with that, I think now we have much better tools. Yes?
I had a couple of questions. The first one was like, you mentioned the graph many times. What does the graph come from? Like, what do you mean by the graph?
So graph is a representation of the robot in a task. No, it starts from a kinematic graph that represents the robot itself, and then it has basic representations of the task the robot is trying to do. So that's the logic part that is added to the graph, and that's fixed for that set of tasks.
The second question was, at what point are you incorporating, you said you incorporate robot kinematics, but then also kinematics of the scene.
No, so we incorporate, more recently we only incorporate the kinematics of the robot as an input. The kinematics of the scene are learned in a separate model, which is kind of a general knowledge, but we are forcing our structure to have a separate part for physics and soft kinematics, dynamics, and and articulation in a separate part of the model. So it is based on physics neural operators. So what it does is that you start with a known equation as much as you can, but then you wrap it up in a loss function so you can deviate from it if enough data is there. So that's the basic idea. Yes?
So Like in real world robots, we call it task, like object detection, segmentation, that's a task. So my question is that doesn't it become a problem that you're streaming camera data continuously, but when the task is called, you only have stream for that when the task is running or it is running?
So it's funny, how many people remember hidden Markov models? All of you do, right? And then how many people remember the long short-term memory 2017? Okay, all of you do. So this is funny that now we are reinventing the same concepts in the agentic interface. So basically, agent is nothing more than a one way to retain memory. So agent doesn't retain memory by itself. It allocates a space in the GPU, but then you can define the memory. So one of the problems with the current VLAs is that the context length is stuck and you can barely store more than a few seconds of data. And then you can do that task at hand, but then you lose memory of the rest of it. So agents provide a couple of properties. One property it provides is you can, in the beginning, define a memory, but you can also do more things on the representation. That gives you long-term context, because agent is, let's say, figuring out what's my next thing to pick up. So it remembers that I have now picked up this box, and so on and so forth, and it holds that. It passes on to a different agent, which will use the same model and say, now execute the motion to pick up that box. So that's called agentic orchestration, and people are doing it in the online world. Like if you're building a financial agent, you will have different kind of agents, but we are doing it in the robotic space, robotic skill level.
I think so. You don't have to stream it again. You can start streaming midway. So you're not streaming all these models at once, right?
No, those are the inputs on the left.
Yeah. So you stream the cameras, and the cameras are streamed on the main VLA model. But the agent, like when it requires the segmentation masks.
So it queries the model. So if you require, in this particular instance, this was for a mobility company, your things are streaming. And this is more of a flat architecture. There's no interaction between the agent. So the pipes come in the frames, and then you say, oh, tell me about segmentation. Another agent says, tell me about the depth. Now, it does happen in one of those hard cases that a dependency query is useful. Just by looking at the left image, it's close to impossible to figure out that there is a car there. So now you have to issue a different, more informed reasoning query, and these agents provide a way to do that. The second thing they do is that they also provide interpretability and modularity to the end customer or the operator or whatever, right? Otherwise, if your model is end-to-end, then you don't know what's going on, right? So I think what we're doing is now picking up a lot of tasks. So the fun thing that we are seeing is we are working with robots that are in production. So we are not spending any money on data collection ourselves. So that's one unique thing about our idea. And this I learned very well from the very beginning, from engineering actually. It's like if you can put this whole data collection on a flywheel, and you can put your releases and your product development also on a flywheel. So every 15 days, and it's better if it's a week. If you can collect more data for free, it's much better. So think about Tesla. The data they collected was for free because people were driving their cars anyway. And that was very smart. So what we're doing is that how do we get fastest to collecting the data for free? So what we have now done is that we have picked up numerous tasks in warehouses, in agriculture, in construction, and so on and so forth, that are not on the bleeding edge, but they're on the leading edge. And then what we do is that we have a model in the back, which is this orange thing. And now the programming for robotics has entirely changed. We are not writing code anymore. Not that much code. We are not writing 100% code, we are writing 20% code. But what we are doing actually is we are writing agents, or we are improving the model. We have two teams. One improves the agents and the robotic solution. The second team builds the model. They're the only things you need to do, I think, in the long term. And what that allows us to do is that you say, okay, what are the agents you need? What's the robotic structure? So on the left side, you have the robot kinematic information. You can simply upload it. You can define a bunch of agents. You have to be a little bit smart about it, how to set up the memory, how to call the model, how to do a few things. And then there's one more layer. I mean, so we are trying to reach a level where operational people or non-experts in transformers can also quickly design solutions, because there's no way in the world that a company of our size, or even if it was a larger company, we could be handling 20 different companies in 10 different industries. But the reason we can do it is because we have productionized how fast we can build things. So this is actually 80% of coding we do for any customer. We're not writing code for a new customer. All we are doing is just using the agentic interface, building the skills. And now what that allows us to do is basically go around and deploy the solution to many, many, many customers. So one customer is a large robot. They call themselves super humanoid, which is very cool. For the robotics, I'm so excited to work with this robot. And it lifts heavy stuff. Like think about furniture, think about these shipping stuff, right? And they have numerous problems that we are working with them, and all goes to the end. Go ahead. Oh, sorry. All goes to solving harder problems, and for in research world, we think that a cardboard box picking is not an interesting research problem. But in real world, the boxes are just very badly packed. They're crumpled, they're not boxes. People get unhappy if their Christmas present comes out in a broken box, right? So we don't want to do that. And then you have to deal with humans and all these boxes. I mean, look at this environment on the box packing. It's a very hard perception and manipulation problem. You can't do that. We are looking into more applications. The airport bags. Why not? It's like how many times we have sit on the plane because the bag didn't get loaded or something else did come. So we are now working with airport operations and many airlines and our partners to automate numerous operations. But also more importantly, I don't want to sit on a plane for 30 minutes because of the ground staff. It's not the labor problem. It's that if it's cold and windy, by regulation, you cannot have a person. It's not that the flight cannot land, that they don't allow it to land. Flight can land. The problem is if the ground staff is not available to do certain things, they stop you at the origin airport. So there are many things why flights get late, right? So now these are the kind of problems we are solving, right? So this is one of the relatively medium grade case where every box is flat and stable. Don't see any crumpledness. But that's not the average case, right? This is in real world things get different. Construction. So this is a company called Canvas Construction that we are putting in production. This goes around and makes walls. So if any of you have ever done any construction work in your house or help, you will realize how hard it is. And one thing we are constantly surprised about, things that seem very easy are very hard. It's so hard to make a flat wall. Like when you see a worker coming in your house to make a wall flat, and if it's a museum grade, commercial grade wall, which is 3 stories tall, think about how much 1 degree can cause the wall to shift and unevenness. It looks really bad. And those are the places where we are building it for. Now this becomes a precision job, because you have to really intricately figure out what is going on. You have to figure out how to put the mud, paint it, and so on and so forth. Now we are not doing the hard part. Canvas is great. They're building the software, they're testing it, they're building the AI to do certain things, but we are helping with certain parts of AI. And this robot then goes around and puts the mud on the wall, scrubs it, puts the paint, smoothens it, does a bunch of things. And it's in some sense, it's a different kind of a job. You have precision, and understanding is more important. But the nice thing is you have the same model. You just have to query it differently with a slightly different input case, and physics really helps. Then we're working with large heavy equipment companies where you are driving these machines to do certain tasks. Now, in farms, mining, and a few places, you're not trying to go from point A to point B. The reason you are doing these machines is they have this implements at the back, they call them implements. They scoop mud, they collect your crops, they collect the fruits, they do something. So there is a more detail to it. And then you are doing basics of operations, and some of it is navigation, some of it is safety, some of it is crop intelligence. Like we all hear about stories about how much water is wasted in almond farming and this and that, right? I think it's a logistics unoptimized problem. You have one irrigation line running, you have no idea where to put the insecticide, what to do, and now robotics will revolutionize it, because you can have targeted irrigation, you can have targeted insecticide, you can have targeted tractors doing things, which is not just replacing a human, it's augmenting human ability, which is very exciting. And we have been able to solve some very, very hard problem which would have taken $20 billion to collect data and solve, but what we are doing is with much, much fewer, 1,000x, maybe 10,000x more efficiency, we are able to figure out how to operate these machines in the field. This is one example where, quick question, which one of these images areas the tractor can drive? This is a rhetorical question, so the answer is none of them, because there's a human in both of them. So in some of the cases, we are seeing superhuman capabilities of the AI that we are deploying. It's one of them, it's hidden behind that, the other one is hidden partially visible. Airports again, think about every time your plane leaves the gate, there are 3 people circling the plane. One touching for knobs, one touching for dents, third one looking around. Every time you receive a package on which a metal block is missing, there's a certain percentage of chance that it's on the gateway. And when the jet engine runs, that buckle flies like a bullet. So there is a job of people on the airport to just do something called detecting those pieces, sweeping them out, and that is what is making flights so expensive. And flights don't run not because pilot is not there, because the flight is sometimes because of ground operations. It's just surprising how many times that happens. Port logistics. So when we are working with in rail yards and so on and so forth. By the way, our partner here, Coast Autonomous, Pierre Lefebvre, he told us that this is the best day that cameramen wanted to come. None of the days in the Midwest look like this nice in the weather. You are driving these robots in rain and snow and night, and these robots are driving around in these difficult environments, right? So what we are helping them is with certain intelligence that helps the robot do certain things. So I can't tell too much, but I'm very excited about how we can take it forward and even do more, right? So we are also starting to work with other tasks such as dexterous manipulation. Now I think the humanoids are a upcoming thing, but there are some nice capabilities of different robots. But the bottom line story is, if we are able to use data intelligently, that is, in my opinion, the only way to make physical AI succeed. You can throw $1 trillion to collect data blindly. That is not going to solve the problem that some of the people are thinking it will solve. It will create good demos. It will raise the real estate prices in the Silicon Valley, but it will not solve the physical AI problem. The only way the physical AI problem you can solve is to use data intelligently. And the intelligent way to solve that problem is not putting physics as an afterthought. Okay, I have this model, I will do a voting, or I will try to feed it in a constraint. The next iteration for physical AI has to have physical AI as the real backbone. And we have just taken first steps towards it. There's a lot more to do. And what that does is, whenever you do a cross embodiment, whenever you take a new task, you can actually operate the way ChatGPT does today for new tasks. But physical AI, you need physics, because now if you have learned how to do one thing and you understand the physics, you can actually reason about, oh, I have this gripper, but instead of that, I have a different type of a vacuum gripper. You don't need to actually learn from 10,000 examples that a vacuum suction gripper grips from the front, parallel gripper grips from the side. In some sense, it's obvious common sense information. And common sense information is the hardest to learn, by the way, for AI. And that is what physics could allow us to do and unlock these massive opportunities in different spaces.
All right, thank you for the talk. We have some time for questions.
I was curious how you think these methods should indicate changes to the way that we design robots and their morphologies.
That's such an interesting question. One reason why some of the partners that we are working with are using our method is to actually like an oracle for the future design. So they're very confused about, and it's very hard to say, should I put 3 cameras, put it on the wrist, put it like this? But the latest advances by NVIDIA simulation or our techniques can actually accelerate that end-to-end robot design, which is the hardest because it has sensing, control, and that's a very nice thought, yeah.
Thank you for the nice talk. So what would you recommend for students who want to study VLA or like work on VLA? Like from your perspective and from your experience with these applications, what would you recommend the students to look into?
Right. I think look, there are a couple of wrong ways to do it. One wrong way is to not use VLA. You have to use VLA or some version of it, some large model. The other wrong way is not to use physics. I think the right way is, and this is a great opportunity, if you're able to find techniques, in my opinion, that marry the learnings from robotics. We have so much information on how memory works, right? Like think about it in robotics, the concept of memory has been around for 20 years at least. We have these filters, and for the whole generative AI, memory is new. But if you marry the two techniques together, because robots are operating in context in the real world. So I think those mathematical techniques or conceptual techniques on how to put it together could be very interesting research directions.
Thank you so much for the talk. Curious about any regulatory concerns that you all are having to mitigate, like back to the aviation example you gave. If, let's say, the FAA comes in and says that, no, we also need human in the loop in addition to the utilization of AI systems, and curious how you all are navigating that.
Right. There's a very difficult problem on regulatory. In my previous company, we dealt with the FDA because of the nurse workflows. So one thing we learned is there are certain things which are very sensitive. As an example, if you say I'm going to use a radar monitor in ICU conditions to detect if someone has a problem, I'm changing the topic to healthcare, that was a problem. But if you're using it to inform yourself, that was okay. Now, what it implies in robotics is it actually depends on the use case. So the best business examples are the one where you don't have a hard limitation on regulatory approval. So one example on the airport case is we decided we will only operate in the gate area but not on the runway. Another company was thinking of cutting the grass on airport, which is a big deal because if the grass is not cut, apparently aircraft cannot land and something happens with the radar, grass gets very tall, right? So the grass cutting, if you do in non-runway areas, then you're not hitting certain regulations, but in the gate areas, they belong to the airline, so it's easier to make it in. FAA is still involved, but they don't have a very high bar on doing those things. And similar examples we are seeing in warehouses and factories. It turns out in warehouses and factories, machines are not new. You have moving parts, you have forklifts, things happen. There is the concept of a cell. So if you marry or you take those concepts that exist in regulatory world and either operate within or derive from it, it becomes possible to do it within, and we should do it within regulatory frameworks that exist. Yes.
So when you mention that you are accommodating for cross embodiment, basically inside the VLA, to what level does the motor, are you also incorporating what is the torque on the motor, all that inside the model so that the output trajectories are actually consistent, or how do you handle that?
I think the perfect ideal encoding or embedding for the motor controls don't quite exist yet. But at the very minimum, we are doing something, we have improved something, and are still using it in the same, calling it Go space. So it goes into the model for information. So that's the model part. But we are also finding that none of our partner customers want an end-to-end model. They don't want to have camera as the input and the motor control torque as the output. And the reason is actually going back, it's regulatory. There are 40 years of these large motors, not everything is a small robot, which are certified by someone, FAA or large machinery standards with PID controllers, which work great. So what the agentic framework allows us to do is to have modularity. So instead of having motor control as the output, you can use the information, that's fine. But you don't need to literally connect a VLA to the motor. You can harness the output at different levels.
What is the physics that is going inside the motor? It's just a VLA engagement, but what is the physics that is going inside?
Oh, so that's a different question. So the physics that is going in is that one robot may have one type of sensors, like a proximity capacitive sensors, for example. Second one may not have it. It may have just the torque, 60 OF torque. Now, how do you still use it that it works? You want to minimize the training data, right? So the kinematics, dynamics is one type of physics. The other type of physics that the model is using is the tools, like the inverse kinematics I was talking about. So instead of giving a random output, it can verify certain outputs much faster inside the model. So the model is not a fixed VLA model. What we are doing in the graph AI is the model itself is architected or expressed over the graph. So this physics is getting encoded at numerous levels. So imagine a model that is trying to reason about this particular architecture. The model itself will be expressed over the graph. But maybe we can take that question later. Yeah. Yes.
I just wanted to ask about your experiences training models, because I know like training models that work just end-to-end data to motor, you have to spend some time like tuning it yourself. But with these physical models, are they more or less difficult, I guess? What are the things that you specifically, I guess, need to adjust in your pipeline in order to get these models to work? Like, do you have to manually define, in your scene, specific areas that, are hinges and some areas that are, rotating, I guess, yeah.
No, I think there's a line in the sand that you have to draw. In one case, you can give all the information about the world, but that's not what you want. So what we are doing currently is the only thing we require is to upload the robot file, which tells about the kinematic structure of the robot, the sensor configuration. That takes a few minutes to upload and another few minutes, maybe 10 minutes to process. You're not doing anything else after that. But the model structure, the way it is designed is, we have separated out the tools, operators, a separate part of the network that VLA can access to target new tasks. So yeah, go ahead.
So you said earlier you said you trained a different network to represent things in the scene, right?
So there's a certain stage where a new type of input comes in from a new robot. Mm-hmm. You again pass it through what we are calling as a demultiplexer or multiplexer. It trains different part of the network. So the actual training data may be coming from online videos. It may be coming from certain parts of the network. It may be coming from different modalities. So that is passed again through these transformations to the loss function of the model. That is why what we are not doing is, for each new robot, you are training exact imitation learning end-to-end. Because in our mind, that's ineffective. Right? You are doing it 10,000 times at least. Our goal is, with just providing the robot information and architecting the model in a way that it has capacity to learn physics, can we now take any new task and get it working with 100 training examples? That's the win. Because that 100 training examples you can collect in half a day, 10,000 or a million is a one-year project.
So one of the things I've been thinking about with your interest in physics-informed VLA models is that you mentioned the example of a capacitive sensor, force torque sensor. Okay, let me add some more. Microphone, audio sensor, and so on. One of the things they all have in common is a salience when something important has happened. So you mentioned physics, a kinematic model. When you take your hand and you put it down on the table here and slide it along the table, what's happened is that your kinematics have changed in a way that's important. And because your hand is now guided by the table. Okay? All those sensors just mentioned are very good at detecting that event when it occurs, to an extent that you may or may not be able to pick up with vision or LiDAR or other things. I don't know if you have come across any of that in your work.
That's a very good question.
What I'm really getting at is it's a particular category of physics that has to do with important events that occur during a task, which can be picked up with multiple sensors, but more so with sensors that are kind of more time-oriented. This is also like, when you and I watch a video conference, if the internet connection is not very good, garbled audio is much worse than garbled video. We tolerate choppy video much better.
And this is where I think there's a lot of research needed to answer the previous question, and combining it with the question, we have taken only initial steps. So the way we are encoding, anyone is encoding these models today is very basic. We are converting that into a spectrogram, we are feeding into a tokenizer, some people are doing something smarter, but what you are saying is that all data is not equal. So we have one research direction to say, how do we build better embeddings? To answer on the physics concepts, it's actually very surprising. Some basic physics does not exist in VLA, if you think about it. The fact that I have this, it does not pass through this table, right? It did not go through the table. It's obvious, but does a public VLA has that understanding? The answer is probably not, right? So that is what we need to do research on, because this physical world is very, very interesting from some of these concepts.
I had a question. You showed the dexterity superhumanoid picture, and we had a nice presentation from Dexterity a couple months ago about their stack. Seemed to be like a mix of kind of a modular, some model-based, some learning-based. And I was wondering, kind of, when you're working with a robotics provider like Dexterity, that kind of has an existing stack, where do you find the value add for your framework there within like a pre-existing robotics stack?
Right. I think maybe in some amount of time, we will almost never write code. So I had some discussions, we will be all outcome-driven. So the traditional software, which is if-else and combination of model and old school models. So, okay, let me take a second. That's a very good question. So I'm answering in a different manner. So in the last decade, the way industries wrote software was write the software framework, and AI was within the software framework. The way the robotics and most of the industries will actually evolve is that AI will be the framework. You may have some small pieces of code embedded within it. It's going to flip. It is flipping. Now, to answer your question, how we work with Dexterity, they have that exact framework. They have a software framework. They have different modules. Some of them are ML-based. Some of them are hard software-based. And as they presented in the public presentation, so our approach is, in the beginning, to provide these agents which are augmenting or replacing some of them with very clearly defined boundaries. So as an example, they could be having difficulty in some complex situation humans walking around. So that's the environmental awareness module some company may or may not have. So we add that to the model, right? Later on, we add another model for another company. But the fun thing happens is, I don't know how many have heard of the model context protocol. When you have multiple agents there, the older modules are talking in well-defined APIs. But as it evolves, now agents can talk in latent information, either via MCP or some such framework. So the two agents now suddenly become smarter than more. So our strategy is first work with the customer and see which module or agent do you want to replace or augment, and slowly work with them to unlock more use cases.
Yeah, so maybe one more question for me. I was curious if you could provide a little bit of your perspective about new trends in robotics. So what excites you about the latest and greatest from the field of robotics that you think might be most impactful in the field, from world models to reasoning models to simulation? So what do you think it will really stick?
I think robotics as a area is going through vertical robotics to stratification. So, which basically retreading what we talked about, which is earlier everyone was building their own stack. All the way from hardware, software, controllers, to software architecture, to application, to AI, to testing, and so on and so forth, right? There was a little bit of that happened with ROS or ROS2, where you have the software architecture as a kind of a library or a platform, but that's going to completely flip. So now what we will see is more and more of service companies. So you are seeing companies that will provide testing frameworks for robots. And that is often overlooked in research, like how much time is spent in just testing the robots in the field. You're going to see model companies like us. You're going to see deployment testing support companies. So if you deploy something online on a server, there are now 50 providers that tell you how to easily parse logs with the press of a button. But nothing like that quite easily exists in robotics. So now that stratification, what that does is that it becomes easier and cheaper to do things, not just because of AI, but also because now it's possible to do it that way. So on the application side, what is very, very exciting is it's possible to now build an AI company because AI can do a lot. It's possible to build an infrastructure company because now a bunch of people can use it. And for the application builders who are very excited, they don't have to spend 7 years struggling to do everything. In robotics, one of the venture capitalists I heard is you have to do 10 things A+ to make a company succeed. So think about that. So now what I'm excited about is that when we are working with so many new startups, companies, big companies, and small companies, they can get to production within months. You know, like you can machine a part, you can buy, and that's I think what's exciting me. Now on the research side, I think there's a great progress on VLAs. There's a great progress on latest school of models. But it has also opened new opportunities, which I don't think larger companies like Meta and of the world will solve, and they relate to figuring out how the spatiotemporal sensor data should be used in robotics. They're not going to figure out how some other robot form factor, how do events happen, causality happens in the world, right? So a lot of these things really is a good start, but that by itself you have to augment it with the real world information, and we haven't solved anything, right? Like we are just taking first steps, but that's where I think the research directions will be so exciting.